Let's get it.
Hello, today we worked with the Tradesy list dataset. My name is Rowan.
I'm John.
I'm Jason.
And I'm Brendan.
And so first, our predictive task. Very simply, what we wanted to do here is we were given with a data set that has users and whether they bought items, sold items, want items, or are currently selling items. You can kind of think of this as like an Amazon type website, and we collected data from there. And so our goal was we wanted to predict whether a user U will want an item I. And so how we did this is first, obviously, this data set was stored in a JSON format where one line was one user record. And we wanted to, first of all, implement helpers to automatically detect the gzip versus plain text, iterate through the user's records safely and efficiently, and then optionally limit the number of users for quick development. And so some key functions we have here are the open maybe gzip, which detects gzip magic bytes and opens files in the correct mode, as well as iter users, which stream users records, parses the JSON and skips malformed lines. And so ultimately, this gave us an output of a data set that was ready to be worked with. And so given our goal of wanting to predict items that users want, we had to get positive samples, and the positive samples are pretty much whether a user wants an item. And the negative samples are a little bit more complicated because you can think that if you're a shopper on Amazon, if you put maybe a snowboard in your bag of stuff to buy, there's literally millions or even billions of other items that you're not currently interested in. So that would make it that would give us way too many options in the negative sample. So what we did was a balanced negative per positive ratio of 4, which means that for every positive, we randomly sample 4 items that the user doesn't necessarily want. You can see that here in our sampling procedure. And so ultimately, this gave us over 2 million training pairs with that label distribution of that 4-to-1 ratio.
All right, so now we're going to go into section 2, which is exploratory analysis. So to begin our project, we first had to understand the structure of the Tracy list dataset. And so one of the first things we looked at was the scale of the data. We have around 128,000 users and over 350,000 items. That already tells us we're working with a fairly large e-commerce style data set where user behavior can vary a lot. The key question was how many items do users actually want? And to answer this, we calculated the number of want items per user, and the histogram on the right shows the distribution. What stands out is this extremely skewed or long-tailed pattern. Most users have a very few want items. The median is literally one item, but then we have a small group of highly active users with hundreds or even thousands of wants. The maximum is over 2,300 want items for a single user. This imbalance is important because models will learn differently from users who interact a lot versus users who barely interact. It also hints that a simple average doesn't tell the full story. The behavior is dominated by a few power users. And so on this slide, we dug deeper into the structure of the data set by breaking everything down more precisely. We have 128,000 users, 352,000 items, and over 880,000 total interactions when combining bought, selling, want, and sold lists. If you look at the list type count, want is by far the most common type of interaction with about 458,000 events. That makes sense because users mark many items they're interested in, but they obviously buy and sell far fewer items. Next, when we look at the distribution of want list sizes, again clipped at 100 for visualization, we see a mean around 5.8, but a median of 1. That gap highlights the skew we saw earlier. And something worth noting, 474 users have over 100 want items, which makes them super active users who can strongly influence model training. Finally, we built some pre-processing structures, user list, which is for quick membership checks, global items, which is the full item universe, and item want popularity, which how many users each want each item. These structures help us with efficient negative sampling and feature engineering later on. Essentially, this slide sets up the foundation for everything that comes after. And so once the exploratory analysis was done, the next step was transforming the data set into a form we can actually train models on. The data set originally has a nested structure. Each user has 4 different list items. So the first thing I did was flatten the structure into a simple interaction table with 3 columns: user ID, item ID, and the list type. Flattening makes the data set consistent with how most recommender systems represent interactions. After flattening, we built the efficient lookup structures. These are essentially pre-computed dictionaries that allow us to quickly answer questions like, does this user have this item in their bot list? How many users want this item? Or what other items has this user interacted with? These lookups are crucial for both negative sampling and feature computation. Without them, training would be too slow. Next, to construct a supervised learning dataset, I focused on users with at least one want item. That gives us clear positive examples for each positive interaction. We sampled 4 negative ones by picking random items the user has not marked as want. This 1-to-4 ratio helps balance the dataset while keeping it manageable. Lastly, we split the dataset to 80-20 into training and validation, making sure the positive to negative ratio stays consistent. This sets up a clean and reliable foundation for comparing different models.
All right. In this section, I'll be talking about how the model was designed, including the feature engineering, the baselines we compare against, and why the log regression model was chosen. We'll also connect each modeling choice with the patterns we later observe in the evaluation, so the results will make sense in that context as well. All right. So for the modeling, in this slide, we kind of summarize the 6 engineering features that pretty much form the backbone of our model. So why did we do these feature engineerings? Pretty much user activity features. So users with large wants, large lists of wants tend to be more engaged. So historically, engaged users mark items as want at a higher rate. So including total user items and user want count helps the model capture this behavioral tendency. Then we have item popularity features. So item want pop is one of the strongest signals in the entire data set. Popular items receive wants from many users. So this feature encodes collaborative filtering information without any embeddings needed. And then we have user item interaction history. So this is whether the user has bought, sold, or is selling the item, and it captures their behavioral intent. For example, items a user bought previously often correlate with their future wants. So these interactions help flag the model to understand familiarity and relevance in the model. So why the results happen later is that the model's high precision but medium recoil is partly due to these features, and precision is high because the model makes confident predictions when features strongly align, and recall is moderate because users often want brand new or unobserved items, and the model is conservative unless prior signals are really strongly present. So that's why you might see the results that you're going to see in a couple of slides. But overall, on the right, we have our feature matrix numbers listed along with our training and validation. And again, as Ron mentioned and Jason too, the positive rate is preserved at 20%. Moving on, we have the train and validation split over here, and we pretty much use the 80-20 stratified split And I also included the code so you guys can like take a look at that. Pretty much why this matters is if this distribution wasn't preserved, the model's validation performance could look artificially better or worse. So preserving 20% positives pretty much ensures the model is evaluated under the same class balance that it sees during training. It also means that the precision and recall are directly comparable between the training and the validation. This consistent distribution explains why our validation accuracy and ROC AUC align closely with the training. Um, so moving on to our models, we have two baselines, and the final model that we chose was log regression. So the random baseline pretty much helps us set the lowest possible bar, and its accuracy sits around 50% because the label distribution is balanced at 80/20, and random guessing produces around that number of 50%. And why this result kind of matters is because it ensures that our other models provide real predictive power, and the random ROCAUC of 0.5 confirm that there's no ranking ability because it's a random baseline. And the advantages and disadvantages are listed on the slide. Um, Moving on to the item popularity baseline, pretty much the item popularity baseline predicts wants based solely on item one pop. And the reason that this works so well is because popularity is inherently a collaborative filtering signal for people. If something's popular, people are going to want it, as I said. So it has a high ROCOEC of 0.8733, which is surprisingly really competitive. But the reason why it fails on other metrics is because it completely ignores individual performance, and it rarely predicts positive for low popularity items. And that's why the precision and recall is low. Um, and finally, the model that we actually picked was log regression. And the reason why that this model was our final, and the reason why we picked it is because it's the central model of our project, and it scales extremely well to millions of samples. It handles mixed feature types really well once scaled, and it produces probabilities which are critical for ranking tasks like recommendations, which is what we're doing. So it is interpretable, and it lets us understand why it predicts want or not want within our user. And it's the final model that we predicted, and we're about to take a look at the results soon over here in the evaluation. So pretty much I'm now going to connect the modeling decisions with our scores and explain everything that we have evaluated. Basically, we use multiple metrics to measure all three of these models. We compare random, the item popularity, and log regression using accuracy, um, precision and recall, F1 score, which shows the balance between precision and recall, and ROC AUC, which measures ranking ability, which matters most in recommendation. So by combining these, we gain a complete picture of the model's strength and its weaknesses. So we can move forward. Um, Basically, here's our final evaluation. Um, Comparing all three of the models. As you can see, the random baseline accuracies sits at a zero point 0.5, along with the ROC-AUC as well. Popularity baseline ROC-AUC is of 0.8733, and the log regression results are also listed over here, which happens to be the best overall model. And the reason why log regression behaves like this is because when the model says want the user features plus item popularity plus the interaction flags all align, and these strong signals reduce false positives, and that's why our model performs so well. The high ROC AUC is because the log regression ranks items almost as well as the popularity baseline because popularity is already such a dominant signal, so the model simply personalizes it. This explains why LR gives pretty much the best overall popularity. Sorry, the best overall balance, despite popularity having slightly higher AUC. So looking at the summary comparison, these are all our numbers. Again, we touched upon all these numbers already, but pretty much the results make sense given our current structure of the data set because random is chance level, popularity reflects collaborative filtering and ranks well, but we can't really personalize it, and log regression integrates user behavior, item popularity, and history, giving us the best mixture of accuracy, precision, and F1. And this is important because it shows combining behavioral features with popularity gives significant gains in accuracy and precision while still maintaining strong ranking performance in our model. Moving forward to our ranking metrics, uh, pretty much in recommendation systems, ranking matters more than predicting a binary label. So we compute precision at the top case suggested items for each user. So why log regression achieves, or LR, whatever you want to call it, um, is at P at 5, we have a 0.2552. At P at 10, we have a 0.2264. These scores are meaningful because the model leverages popularity to push high demand items to the top and uses user and interaction features to refine personalization. This combination explains why we achieve over 25% correct wants inside the top 5 recommendations, which is competitive for a sparse behavioral data set like this one. And finally, the interpretation of the results is that um, it kind of ties the entire evaluation together. And why each model behaves the way it does is because random's baseline has no signal, so it's chance performance. Popularity is strong signal, high ranking power, high AUC, but lacks personalization. So we have um, lower precision, and log regression merges the popularity with individual user signals and boosts precision and F1, which maintains near optimal ranking quality. And some key behavioral insights are that users with very large want lists behave differently. Their actions are less predictable. Items appearing only in bought/sold lists behave differently than typical want items because this means that the interaction flags capture meaningful behavioral differences, and these patterns help explain the deviations in precision or recall and ground the model's behavior in real user item dynamics that we see in the scores. And here's a look at the code that we used. And yeah.
Now for our final section, section 5, we discuss related work. So Tradesy functions like an implicit feedback data set, similar to Amazon or MovieLens. So instead of ratings, we rely on behaviors, so purchases, clicks, and wish lists to understand user intent. These data sets are common in e-commerce, recommenders, and collaborative filtering evaluations. For similar tasks, past work often uses matrix factorization, BPR, neural collaborative filtering, and feature-based models. Our results show that Tradesy is best treated as an implicit want prediction problem. A random model gives us the lower bound, and item popularity already carries useful signal. Logistics regression performs the best overall, meaning the features user activity, item popularity, and interaction flags capture real structure in user behavior. There are a few limitations. So negatives are sampled items the user may never have seen, and we don't have timing or exposure information. So for the next steps, we can try implicit matrix factorization or BPR to capture latent factors and use harder negatives like popular unseen items to make training more realistic. Thank you.
Thank you.